effectively this goes very much up, right? The numerator goes up dramatically, the denominator comes down dramatically. See how nature has given you very nice equation where everything that you can explain why is surface. Now when somebody asks you why does reaction rate increase when surface area increases? That's the answer for it. Okay? So Gibbs free energy explains to you the effect of surface area and volume in reactions. Okay. And then further expansions with if you have latent heat of fusion, if you have solidification, if you have, I'm doing cold weather concreting, my water is likely to turn to ice. I have freezing and thawing problems where I may have ice formation, or I'm having a melting of certain things in my system, then you have to modify the equations with all of those, but we won't worry about that. Nucleation rate also is important, number of stable nuclei. This is what is called the Arrhenius equation. These are the kinds of equations that this guy got the Nobel Prize for in, I think, 1916. Arrhenius Nobel Prize for rate of reaction, not for cements, but for general rate of reaction. Frequency at which atoms are from liquid attach themselves to solid nucleus. Now this is also very important. We like to do everything deterministically, right? As engineers, we like to be very certain, right? All of us, right? We want to know the outcome of a process. As engineers, it's natural. We have been trained to be very quantitative. When you tell me that this will happen, I'll get strength, you want to know exactly what is the strength. Will you let me tell you, yeah, you can get anywhere between 20 to 60 megapascal strength for this concrete. Will you accept if I say that? No. You want a number. You want to tell you want me to tell you that you will get 40 megapascal, right? We want to be certain. But think about the processes that are happening in 5, 10 micron particles. If I take a cubic meter of concrete or cement paste, you have billions and billions of these particles, right? Then would your deterministic approach work? You have to do some kind of a probabilistic approach. What is the chance that this might be? Again, you have so you will see that, right? If you take a cement paste, cut it, polish it, put under a microscope and look. Oh, you can say, oh, I mixed this paste so well. I mixed it for 2 hours. I mixed it so well, I made it homogeneous. Can you tell me, looking at the microstructure, can you tell me that every cement grain has hydrated the exact same way? No. Some cement grains might not have hydrated. Some of them would have hydrated so much. Some of them would have formed Hadley grains, right? Some of them would have formed some other compound. Some of them would have hydrated from outside. Some of them would have hydrated from inside, right? So all you can do in such systems, while we do global averaging, we all do that, right? But you should know that when you deal with fundamental materials, global averaging sometimes is very dangerous. It's like saying, what's the average depth of the river Ganges?